All right, so welcome to lesson 8C. Today we're going to talk about confidence intervals and hypothesis tests, but now for two proportions. Remember, inference is either a hypothesis test or confidence interval. It's the process of taking what's true for a sample and using that to come to some kind of conclusion about the population. For a two proportion problem, we are usually looking at the difference between those two proportions. So we're looking at a confidence interval to estimate what the difference between the two proportions might be. For a hypothesis test, we're looking at basically, do we have evidence of a difference, or do we have evidence that one group or one proportion is bigger than the other? So that is what we're going to do today. So I first wanted to remind you of our steps for a inference problem, right? The same steps that we use for a one proportion Z interval and a one proportion Z test can also be used for these types of intervals and tests. It's the same basic steps for any type of inference procedure. What changes is just some of the little details. So let's first remember what the steps are for each type of inference procedure. So for a confidence interval, you're going to define the parameter, check conditions, calculate the interval, and then interpret the interval. For a hypothesis test, write hypothesis statements, check conditions, calculate the z-score and p-value, and then write a conclusion. So let's go into some of the differences. So obviously the details are going to change slightly for a two proportion problem compared to a one proportion problem. So for conditions, we have the same three general conditions, but some of the details within them are going to change because we're now dealing with two separate groups as opposed to just one group. So for our first condition about random sample or representative sample, we now are checking for two random samples or representative samples. But we also need to know that these two samples are independently taken. That is important because we want to make sure that one group is not influencing the other, because if they are, then it's really not equitable. It's not fair to really talk about the difference between the two because they're affecting each other. So the two groups should both be random representative samples, and the two groups must be independent of each other, meaning they were taken separately, they're not in any way related or connected, etc. A lot of times that's given, but again, sometimes we have to assume that in order to move forward with the problem. Second condition typically is the 10% condition. This is testing for independence between trials, so as I'm taking my sample. So this must be true for both groups. So again, that does mean that we check it for both groups. We want each sample size to be less than 10% of their respective populations. And then my third condition is the check for normality, otherwise known as the success-failure condition. And again, we have to check this for both groups. So in other words, for the first group, so N1P1 is greater than 10, and then N1Q1, and then also N2P2 and N2Q2, R2D2, etc. Sorry. For a two proportion inference problem, it's sometimes easier to think of it as the number of successes and the number of failures. And we'll have a couple of examples where that is the case, where you may not have to do any actual calculation, just thinking of it as within our sample, how many successes and how many failures, are all of those greater than or equal to 10. One thing that is a little bit of an exception with a two proportion problem or two sample inference problem, many times that those two samples came from some kind of experiment that was done. So as opposed to just data collection, it might have been an experiment. And in that case, as we talked about way at the beginning of the year, in an experiment, we don't always have a random sample. In fact, we rarely have a random sample. And that sample was not like taken from a population of a larger size. It's usually volunteers. So because of that, the way we check conditions is probably going to be a tad different because our goal isn't necessarily to generalize this to a larger population. Our goal is just to test for patterns and trends. So when it's an experiment, we can actually just check two conditions. We're going to check that the treatments were randomly assigned because this is going to create those two independent groups that we need that aren't affecting each other. It doesn't necessarily need to be a random sample, and it's okay to not just skip that. And then we're going to check success-failure condition, which is the third one. We also don't need to check 10% condition because, again, we're not taking that sample from a large population, so that it just doesn't apply. Right. One thing I wanted to just remind you of or talk about is the difference between independence between trials, which is the 10% condition, and then the independence between samples that we check for a two proportion problem that we want to make sure the samples are separate. They're both forms of independence, but we check them for different reasons. So when we're picking a sample from a population, remember we check that 10% sample, or we check that the sample is less than 10% of the population, and that makes sure that the probability of success doesn't change too much from one selection to the next to the next. And we've talked about that with relation to like M&Ms and blue M&Ms, and if you want a reminder of that, let me know. Whereas this is different for checking for independence between our samples when we have two samples that we're picking, right? We want to make sure the two samples aren't affecting each other, because that would invalidate the results that we get. So there is a difference between the 10% rule, which checks for independence between trials, and the independent random samples for a two proportion, which checks to make sure the two samples are separate from each other. So that can sometimes be a little bit of a confusion. It's really like two different types of independence. So let's go ahead and start a problem. We're really just going to do examples today so we can go through the process for everything. I'm going to do one interval and one test, hypothesis test in this video, but I do have one more example of each that's on the end of the slideshow that you can go back to if you want to kind of see another example. So let's start with a two proportion. That should say two proportion. Sorry about that. Z interval. So remember our basic formula, we're going to talk about formulas and then we'll go into a problem. But our basic formula for a confidence interval is the statistic plus minus our critical value, Z star, times our standard deviation. So it's the same idea, but now we're going to estimate the difference between two proportions. So what that ends up looking like, our statistic is basically p hat 1 minus p hat 2, right? We subtract the two sample proportions. Critical value is still Z star. We find it in the exact same way that we did before. And then our standard deviation of the statistic looks like that. This is on your formula chart, by the way. It's kind of split up. They give you, like I said, the generic formula for a confidence interval that's up here, but then later they do tell you how to find the standard error, the standard deviation for different types of problems. And so that's what that looks like. Obviously, there's a lot of math that goes into that. Fortunately, I don't in any way expect you to write out that formula on a free response question. We're going to let the calculator do the work. It's one of the nice things about statistics is the actual complicated calculation generally happens in the calculator and we do the interpreting. I do want to mention that we do need to name the test. So saying two proportion Z interval somewhere on your problem is important because that identifies what type of inference procedure you're doing. And then sometimes the formula will show up on a multiple choice question. It usually does at least once on an AP exam. So it's good to be somewhat familiar with it and know what to look for, but you don't necessarily have to write it out. So let's look at our example. So a survey asked independent random samples of adults from the US and Germany about the importance of brand names when buying clothes. Of the 2,309 US adults surveyed, 26% said brand names were important, compared with 23% of the 1,058 German adults surveyed. We're going to construct a 99% confidence interval for the difference in the proportions of US and German adults who think brand names are important. So we want to find a confidence interval that gives us an estimate for what is the difference between these two proportions. So the first thing we're going to do is define our parameter. Now on a two proportion problem, we have two parameters. So we're going to define P1 and P2. So for me, I wrote P1 is the proportion of US adults who think brand names are important. And then for P2, the proportion of German adults who think brand names are important. You do have the option if you want to define the difference. You could say P1 minus P2 would be the difference in proportions of adults who think brand names are important. You just need to specify like German minus US or US minus German. So like in parentheses at the end, you would put like US minus German or German minus US just to indicate which way you're subtracting, because that's also going to change how you put things in the calculator. So that's our first step, is to find your parameters or parameter. Your second step is to check conditions, right? So our first condition is, do we have independent random samples, or can we assume that? In this example, it says that they did ask independent random samples, so that's just straight up given to us. So I'm just going to write, given 2 independent random samples of US and German adults. So first condition done. Your second condition is 10% rule. And again, we want to make sure and check that for both groups separately, because they're separate groups. So I would say assume that 2,309 is less than 10% of all US adults. And then I would say assume that 1,058 is less than 10% of all German adults. Our third condition is to check for normality. And for that, we check NP and NQ greater than or equal to 10 for both groups. So for this one, I'm just going to do that because we were given the P's as percentages. And so it's easier to just actually multiply N times P. And we'll do another example with the hypothesis test where it's easier to check for successes and failures. It just kind of depends on what you're given. So N1P1 would be, this is for US, so 2,309 times 0.26, which is 600-ish. And then N1Q1, 2,309 times 0.74 is about 1,709. For the German group, right, N was 1,058, P was 0.23. That comes out to about 243. And then for NQ, 1,058 times 0.77, which is 814 or 815. All of those are greater than or equal to 10, so a normal model may be used. Congratulations, us. So yes, it's a lot more to write out because you're basically kind of writing it out for each group, but it's still necessary. So our next step is to actually calculate the interval, and this is where we're going to use the calculator because our formulas are definitely very tricky, and we want to get to the math part faster so that we can interpret it. All right, so what we're going to do in our calculator is go to Stat and then Tests. This is where we were when we did one prop z-test in the last couple of lessons. And what we're doing right now is a 2-proportion z interval because we have 2 different groups and we're doing a confidence interval. So I'm going to scroll down and I'm going to look for where it says 2 prop. So all the tests are first and then we get to the intervals. So make sure you kind of scroll down. We should be looking for 2 prop z int, which is option B. I'm pretty sure it's option B in all calculators, but I can't remember. So option B is a 2 prop z int. And then it's going to ask you for some values. So it asks you for x1, n1, x2, n2. So basically x, remember, is the number of successes within that group, and n is the sample size of that group. Since I defined P1 as the proportion of US adults, x1 and n1 should be about US adults. What makes this problem a little bit trickier is that I wasn't actually told the number of adults in each group who think brand names are important. I was given the percentage. Now I can do that math pretty quickly. I just need to know for the US adults, what is 26% of 2,309? I actually found that when I checked that condition. So it's actually right there. So it's 600.34. But you could also type that in here. I could put 0.23 times 2,309 in that X1 spot and then push enter and it'll do the math for me, except apparently it's 0.26, sorry. But yeah, it'll do the math for me in that little spot, right? And then I'm gonna say N is 2,309. And then I'm gonna do the same thing for X2, which is the German group. So this was 0.23 times 1,058. And then N2 is at 1,058. And then I would put in my confidence level, and it does need to be as a proportion. So for a 99% confidence level, I'm going to put 0.99. And then I'm going to say calculate. And then it's going to say error because this is what the calculator needs. I did that on purpose. I knew it would do that. So the reason it's saying an error is because when you use a confidence interval and you're putting in X, X is the number of successes. The calculator can't make sense of a decimal number of successes. So even though, 26% of 2,309 is 600.34, we need to round that to the nearest whole number in order for the calculator to do the math for us. So I'm just going to round each of these to 243. Right, and now when I go to calculate, it will give me an interval. So I can see that my interval is negative 0.0106 to positive 0.07094. So now I have my interval. Look how easy that was, instead of us having to use that entire formula that we were given. So there's my interval. So on my paper, I would just need to make sure and write the name of the interval or the name of the inference procedure I use. So I would write 2 proportion z interval. And then I would just put in parentheses the interval that I got from my calculator. So negative 0.0106 to positive 0.0709. Right, so that's my third step. And then my last step for an interval is to interpret it. So when we interpret the interval, remember that this interval is giving us an estimate for the difference in the 2 proportions. So when I interpret it, I need to interpret it as a difference in 2 proportions. My interval is partly negative, but that makes sense because sometimes when you subtract 2 numbers, you get a negative number. So a negative part in your proportion or in your interval just means that the difference of US minus German could be negative. And that would mean that German is higher than US, right? So it makes sense that we're getting negative sometimes. That just means that the difference was negative. So the way that I interpret this, there's kind of 2 different ways that I could say it. One is to say it as the first group is either greater or less than the second group, depending on your numbers. And then the other way to say it is just to talk about it as a difference between the 2 groups. It's kind of either way. I like the first one because it gives it a little bit more context, like it makes more sense realistically. The second one's a bit easier to say. So it's just kind of whatever you feel like saying. So I'm going to show you the 2 different ways of saying this for this problem. You can kind of decide which way makes the most sense to you or is easiest for you to write. So one way we could say this is that we are 99% confident that the true proportion of US adults who think brand names are important when buying clothes is between 0.0106 less and 0.0709 more than that of German adults. So the reason I put less and greater is, remember, the 0.0106 was negative and the 0.0709 was positive. So it could be that US adults are 1.06% less likely to say brand names are important, all the way up to, they could be up to 7.09% more likely than Germans to say brand names are important. So that's what I mean by that interpretation, right? It could be anywhere from 0.0106 less up to 0.0709 greater than German adults. Right? So that's one way that I could say this. The other way that I could say this is literally just interpreting it as a difference. So saying we're 99% confident that the difference, US minus German, and the true proportions of adults who think brand names are important when buying clothes is between negative 0.0106 and 0.0709. Right. So that is our interpretation. One thing to note is that if 0 is contained within the interval, that means it's possible or plausible with 99% confidence that there's no difference in the groups, because 0 means that P1 minus P2 is 0, meaning that there's no difference between the 2 groups. So if you were asked a question that asks something like, does this confidence interval suggest that US adults are more likely? Okay. Part of the interval suggests that US adults are more likely. Part of the interval is positive, but part of the interval suggests that it is possible, very possible, that US adults are less likely. And it's also possible, because 0 is in there, that they are equally likely. So if you're asked a question like this, you're looking for, is 0 in the interval? And so in this case, I would say, no. Since 0 is in the interval, it's plausible that there's no difference in the proportions. So we do not have evidence that there's a difference at the 99% confidence level. Now, possibly if we lowered our confidence level a little bit, it would make the interval a little bit narrower, and maybe at that point it would be all positive, but then we would be less confident of that. So it's a give and take. If we were asked to interpret the confidence level, remember we talked about this with 1 proportion z intervals in the last unit. This is where we say what it means to be that much confident. So if I were to repeat this process many times with many different samples, about 90 whatever percent, in this case 99% of the intervals would contain the true difference in proportions of adults who think brand names are important between the US and Germany. All right, so it's just explaining what we mean by the level. When you're interpreting the level, we should never be mentioning a specific interval. We're just talking about the context and the confidence level and what that means. Okay. Remember, that would be an extra question. It's not something that you need to write in every confidence interval problem. All right. So next we're going to go on to hypothesis tests. All right, so now we're going to talk about hypothesis tests with two proportions. All right, so we're going to start with the actual hypothesis statements. So remember, when we're doing hypothesis statements, there are two statements that we are writing. The first is the null hypothesis. So for a two-proportion problem, our null hypothesis is a statement of no effect or no difference or no change. So in other words, P1 equals P2. There's no difference between the two groups. This is always, always, always our null hypothesis for a two-proportion test. We could also write this as P1 minus P2 equals 0 because the difference between the two groups is 0. Our alternate hypothesis is testing some kind of change. So that could be that one group is greater than the other, one group is less than the other, or it could mean that one group is just generally different from the other. So that is based on what the question is saying they suspect is true or what they're trying to show, etc. So I would say something like P1 is less than P2, P1 is greater than P2, or P1 is not equal to P2. And again, we could write that as the difference. So P1 minus P2 is less than 0, greater than 0, or not equal to 0. It will always look like this. One thing with two proportion is that there's not going to necessarily be a number of any kind or proportion in your hypothesis statements. It's all about comparing the two groups. Now, in advanced statistics, we can get into testing for a difference of a specific amount. So we might have something like P1 minus P2 is less than 5 if we thought that they were more than 5% different. But for what we do in this class, for this intro to statistics, we just look for a general difference. Again, if our hypothesis statements are using P1 and P2, the symbols, we need to define P1 and P2, just like we did for a confidence interval. You can also choose to write out the hypothesis statements completely in words. Formulas, if you thought intervals were complicated, tests actually get even a little bit more complicated. So our basic formula for a confidence, this is confidence interval, but should be a Z statistic because that's what we write out the formula for on a test. So our Z statistic is the statistic, so the actual value we're getting from the sample, minus the parameter, and that comes from the null hypothesis, divided by the standard error of the statistic. So for a two-proportion problem, Z equals, right, our statistic would be the sample difference between the two proportions. So P hat 1 minus P hat 2. And then minus, our parameter would be the null hypothesis difference. And if you remember, our null hypothesis is always that P1 minus P2 equals 0. So this part of the formula would always be 0. So really, the top part of the fraction is just P hat 1 minus P hat 2. And then the bottom is where it gets tricky. So our formula for the standard error, the standard deviation on a hypothesis test is actually a little bit different than for an interval, basically because on a hypothesis test, our null hypothesis is that they are equal. So we are just kind of pretending that the two proportions are equal. So we have to find this P hat C, which is basically the just overall proportion of success. And then we multiply that by 1 over each sample size. So it's actually a whole lot more complicated. Again, I don't expect you to write this out. These might show up on multiple choice tests, on multiple choice problems, but actually these aren't super common even on multiple choice problems. We generally see confidence intervals for two proportions, but rarely hypothesis tests. I mean, that might change in the coming years, and again, just make sure you write the name of the test and then you don't really have to show the formula. So let's go straight into our example. So a driving school owner believes that instructor A is more effective than instructor B at preparing students to pass the state's driver's license exam. An incoming class of 100 students is randomly assigned to two groups, each of size 50. One group is taught by instructor A, the other by instructor B. At the end of the course, 30 of instructor A students and 22 of instructor B students pass the state exam. Does this study provide evidence that instructor A is more effective in his teaching methods than instructor B? and we're going to use a 5% confidence level. One thing I wanted to mention here is I always get the question once we start doing all types of inference procedures is how do I know whether I'm doing an interval or a test? So my hint is an interval will always ask you to do an interval. So if it says calculated 90% confidence interval, you're doing an interval. But for a test, it's rarely going to say do a hypothesis test. It'll usually say, does this provide evidence? Or do we have sufficient evidence to suggest blah, blah, blah? So that word evidence is your clue that you are doing a hypothesis test. You'll also sometimes be given a significance level, which is another clue, but the evidence clue is a better one. So first step for a hypothesis test is we're going to write our hypothesis statements. So in this one, I would need to define P1 and P2 first, just like I did for an interval. So I would say, hold on, pause. I thought I changed that. Apparently not. Okay, sorry about that. So I fixed it now. I did a lot of copy pasting. So I put PA as a proportion of instructor A students who would pass the state exam, and I used PB as the proportion of instructor B students who would pass the state exam. One note is you can use letters instead of P1, P2. I said PA, PB because instructor A, instructor B, it made sense. You don't have to do that, but that's there. And then my hypothesis statements, your null would be that the two proportions are equal. So PA equals PB, and we could also write that as PA minus PB equals 0. For your alternate, in this case, we're trying to say that instructor A is more effective, so PA greater than PB, and then I could write that as PA minus PB is greater than 0. And again, it's totally fine to use 1 and 2 instead of A and B, as long as you know which is which. Second step is conditions. So our conditions for this, the first one would be do we have random sample, 10%, and then success failure. Now I do want to note that this one is indicating that we're doing some kind of experiment because they're talking about students being randomly assigned. So this is the one where we don't necessarily have to check all the conditions in the same way. It's not really a random sample. Probably they're volunteers, they volunteered to take the class. So what I would say instead is just that it's given that the students are randomly assigned to instructors, which is creating those two independent groups. It's not really a random sample, so I'm just not even going to mention that because it's really just an experiment. And then again, if it's an experiment, I don't really need to do the 10% rule because I'm not really taking a sample from a population, so it doesn't really apply. So I'm going to go straight to my success failure condition. And this is where I'm going to show you another way that I can do that instead of actually multiplying n times a p. If I know the number of successes, I can just write it as that. So for instructor A, 30 passed. That would be np. If I actually multiplied 50 times 30 over 50, I'm going to get 30. So it's sometimes easier to write it as 30 passed. And if 30 passed out of 50, that means 20 didn't pass. So that would be my NQ. And then for instructor B, 22 passed. And then out of 50, if 22 passed, then 28 didn't. All of those are greater than 10, so we can use a normal model. All right, so that's just another way that we can write that out that is easier when you're given the information in this way. Okay. Third step is to do the math. So I'm going to go to my calculator for that, just like we did before. I'm going to go to stat and tests, and this time I'm doing a 2 proportion z test. So option number 6. I have the same 4 first things, so I want x1, n1, x2, n2. This one will be a little bit easier because I'm actually told that I have, the first group, instructor A, I'm going to put as P1. So 30, and then n is 50. And then for instructor B, 22 passed out of 50. And then I'm testing that instructor A, or 1, is greater than. So I'm going to go over to the greater than P2. And then again, I can choose either calculate or draw. It's up to you. I'll choose draw. I like the picture. It draws me the area of the normal model that it's shading. This normal model actually represents the sampling distribution of the difference in the proportions. And then I have the area that's shaded. I'm told that the z-score is 1.6013 and that the p-value is 0.0547. So now I'm going to write that, right? 2 proportion z-test is naming the test. My z-score was 1.6 and my p-value was 0.0547. And then my last step is to write a conclusion based on that significance level and p-value. So same as we did for a 1 prop z test, same type of conclusion. It's just the way we interpret the hypotheses that are a little different. So I would say, since my p-value 0.0547 is greater than my significance level 0.05, it's not a lot greater, but it is greater. We follow the rules. If it's greater than alpha, we fail to reject the null, right? P is greater than alpha, we fail to reject the null, which means we do not have evidence to suggest that alternate is true. So we do not have evidence to suggest that the proportion of students who would pass in instructor A is greater than the proportion who would pass with instructor B. So we do not have evidence that instructor A is more effective in his teaching methods than instructor B. If we are asked to interpret the meaning of the p-value, right, remember from when we did 1 proportions, we're basically saying, assuming the null is true, the p-value is the probability of getting what we got in the sample or something more extreme than that, meaning further away from the null. So interpreting that for a 2 proportion would be something like this. Assuming the 2 structures are equally effective, because that was the null, assuming the null is true. Our p-value 0.0547 is the probability that we would just by chance observe a different in-pass rates like the one we saw in the study, or a difference even more extreme, so even further away from each other, right? So assuming the null is true, p-value is the probability that we would just by chance get sample results that we got, or sample results more extreme. So that is the end of the examples I'm going to go through in the video. Like I said, there are extra examples, one of each type, one of a confidence interval, and then one of a hypothesis test, just to give you a little bit of extra practice if you want to look at extra examples. But I'm going to be done blabbing at you today because that was a long